So let's now look and put a few things together. Okay, so here is our first example. If you need to pause this whenever you need to. You've got these written down. So you got two forces, 3,500 and 4,750 at two different angles. Well, here's the horizontal. Here's the first one, 3,500 newtons at 34 degrees. The second one, 4,750 at negative 65 degrees. So it's 65 degrees below the horizontal. That's what that means respectively. Just in case you haven't heard that. Two things, usually two or more in a list. First with the first, second with the second. Okay, so in order to add vectors, which is what we're trying to do, we got to get component from them. So here is, it's nice with the horizontal. Here is for your first vector, horizontal component, vertical component, calculate it. Do the same thing with the horizontal and vertical component. Notice though, that one's downward. So we got to make that a negative. We got to make that horizontal component a negative to drop. It would happen with a negative 65, but I don't let the angles do it. I'll let myself take care of it, only because sometimes the angles and our arrangement of how it is and our context could actually make the positive or negative directed from the angles themselves to be incorrect. So I'll just take care of that and treat the components as sizes, and I'll put the directions in. So add them up. So here's the resultant. Again, what really is the resultant? A new vector that goes 4909.07, negative 2347.78. So there is this new vector with those two components. Again, the negative just means it's downward. So when this object gets pulled, it's going to be following this path. That's really what's happening physically. So magnitude, Pythagorean theorem, so that it in fact feels a force of 5441.60 newtons. Direction, again, go ahead, we got the opposite adjacent, we got the two legs of that right triangle. So this 25.6 degrees is this angle here because it goes down. So I'll describe it as a negative 25.6. You could say 25.6 degrees below the horizontal. That works also. All right. So figure. Here's our inclined plane. Here's our bale of hay. Underneath, you can barely see here, is a little sled. So with the bale of hay and the sled, the total weight is 65 pounds. So what we're saying here, that we've got this force pulling up here. Maybe it's got to be hooked up. It can't be hooked up right in line with the sled. It's got to be hooked up above. So it creates a little 20-degree angle from the ramp. Well, first thing is, how much of the weight of the bale of hay and the sled is going to draw it down, and how much is going to go in to holding it? Well, that's this right triangle. Again, the angle up here is the same as the angle down here. So 35, 35. This time our x, our parallel to the ramp, is actually opposite the 35, so that's why we have sine. The weight, straight vertical, times the sine of 35, boom. So that's the force, that's how much wants to go down the ramp. So we take, so I'm just now going to switch gears, now just focus in right in here. So the amount along the ramp, down the ramp. So if we can hold that amount up the ramp, ain't moving anywhere. Well, but it's not along that line. It's not parallel to the ramp. It's at that angle. Well, hey, that's a nice little right triangle again, where we know the adjacent leg of the 20 and the hypotenuse. Solve for f, plug it in. So we only need 39.68 pounds of force to keep it from sliding down. Now it seems like, wait a minute, but the weight's 65. Yeah, but there's a lot of that weight. There's a component of the weight pushing down into the ramp. We don't have to hold that up. Ramp's doing it for us. Okay? So this time you're going from one of the right triangles, using that to get the other piece. Sometimes you're given that force and you could walk your way back to this piece turns out to be the ramp, and then that's the weight. Okay? Pause when you need. Okay. So you got a motor on a component, top speed 12 miles an hour in calm water. That just means no waves. It means there's no current, nothing pushing the boat one way or another. And the boat is in a river, current of 3 miles an hour. Well, one thing to pay attention to is that water and air act the same. So, in fact, fluid dynamics is what the field of study for motion and things like boats, different kinds of keels and things like that for the water, and also the fluid dynamics also describes air movement. So the wind is a current of air as opposed to a current of water. So we treat this as the boat running around 12 miles an hour. We'll just say it's horizontal. Why? Why not? We get to pick the current. Since it's going downstream, that's with the current. They're both positive. Add them up. Okay. Now magnitude, of course, with 15, with one of the components is 0, you don't have to do the work. That is it. Direction, downstream with it. By the way, upstream is against the current, so they would be opposite directions. So now another plane. So one thing, notice here, that's the math style. I call this physics style because in physics this is the way we usually do X, Y, or something like that. Sometimes you put horizontal or vertical. That's one of the different options you can use, kind of thing, for physics. I'm good with either form, but label it. Don't just put 12, 0, 3, 0, 15, 0, because that don't mean anything to me. Labeling, then it does. So here, let's do this physics style, so we won't need little things there. Okay? So, physics style. X, Y, horizontal, vertical, or east-west is the horizontal, north-south is the vertical. Doesn't have to be, but we just have this. So, wind's blowing out of a bearing. Actually, it should be to a bearing. I actually did to a bearing, so these should be negatives because it should be this way. Bummer. Planes flying due east. Anyways, let's just, if we change this to a bearing, so towards that direction. I didn't read it. So, same setup. So here's our plane. Due east, straight east, no north-south component. Wind, make your triangle. Components, add up the x's, add up the y's, east-wests, north-souths. And then the ground speed is the magnitude. So when you're looking from the ground, how much ground is it covering with or without, with the help or hindrance of the wind? Bearing. So if this is the direction of the plane's flying, so the plane's flying this way, regularly wants to go this way, wind's pushing it up a little bit. So bearing, you get the angle of the triangle, but because of the format of the original, we need the angle from north. So that's 83.2 degrees, and it's to the east that amount. Okay, I may go ahead and make that correction on these and put that up later. Okay, well, you can do the work, try it, see what you get. Okay.